super excited to be talking again at the AutoML conference. Last year, we also gave a talk on AutoGluon, and a lot has happened since then. Also, I gave a talk at the Fall AutoML School, which was a pleasure. So I'm here today with other members of my team, Alexander Schur and David Salinas, to talk about the work towards AutoGluon 1.0, which we're planning to release in November this year. And what does it mean for an AutoML system to be 1.0? What are we hoping to achieve in that release? And how are we trying to incorporate some of the latest advances in machine learning into the system? All right, let's get started. So let's talk about the agenda real quick. I'm going to start off with an introduction to AutoGluon as well as AutoGluon Tabular. Then I'm going to hand things over to Alexander to talk about multimodal and time series. Then we're going to do a quick hands-on tutorial. Then I'm going to talk about the things coming in AutoGluon version 1.0. We're going to talk about a specific thing coming in 1.0, which is AutoGluon Zero Shot, which I'm very excited about, which David Salinas will be covering. And then we will finally have time for Q&A and feedback from the audience. All right. So in the Discord channel for this talk, there is links to the hands-on tutorials. If you would like to go along, I will be doing it live as well, but there are links there. And basically, I'd recommend when you get to the Colab notebook, basically run the first cell, which installs AutoGluon, so you don't need to wait on that. So, you know, as is tradition, let me go and do that right now. Boom, and run anyway. All right, there we go. Now, so let's talk about ML in a nutshell. So in general, you know, in very simple terms, machine learning is bringing your data, could be tabular, text, image, all of it at once. Then you want to use your data to do something, and then hope that that thing ends up being able to make predictions on new data that is useful to you. This is really the simplest nuts and bolts description of machine learning. Of course, there's a lot of nuances here, but a lot of times what people care about is this exact series of events. So here is what I think are 7 steps to an AutoML revolution. I talked about this at the Fall AutoML School a bit, but I'm going to reiterate it. So in order for AutoML to become the golden standard of machine learning in practice, basically, in order for people to gravitate towards AutoML as the first tool when working on practical problems, I think that we need to satisfy 7 things. 1, it needs to be easy to use and widely available. It can't take a week to get started, right? So you better eliminate basically every possible hurdle and make it in as few lines of code as possible. It needs to have strong performance. Now, again, we talk a lot about what does it mean to have strong performance, and I would say that relative to anything that isn't AutoML, we should be better in general. So it should be the case that if someone uses AutoML, they are enhancing their capabilities rather than limiting themselves. It needs to have fast inference speed, basically fast enough to be able to solve the practical problem without basically making it so that it isn't usable in a real-world scenario. So for example, if someone needs 50 millisecond end-to-end latency so that it feels snappy and real-time, then your system better be able to accomplish those criteria to be usable. It needs to be stable and reliable. It needs to work. If you scale up to a large enough data set and it starts crashing, if you add missing values and it starts crashing, you know, if you start changing your Python version or changing your operating system, right? Things need to work, and they need to work in a wide variety of scenarios on a wide variety of data. So make sure it doesn't crash. It's actually quite hard, but it's necessary. Next up, customizable. It can't just be this one fixed thing that always does the exact same thing. Like, that's nice and all if it works well, but at a certain level, you're going to want to have some customization options. For example, maybe you have an in-house model that works really well, And so you want to incorporate that within the AutoML system and tune that model, or basically ensemble that model with other things. You want to give the users the ability to do those kinds of things. And this also goes into play of when you are doing open source work, right? By being open source, you are allowing people to tinker with things, to edit them to suit their needs. Interpretable. We talked a lot about that, didn't we? So interpretable is a complicated subject because what does it really mean to be interpretable? I would say that interpretability is about providing users the information they need to be comfortable with the solution that you provide them relative to them having it done themselves, right? And so this is a bit of a subjective area, but things like feature importance via permutation shuffling, Shapley values, etc., are all good points to have here. Deployable. Once you have trained it, you need to be able to use it. And you need to be able to use it at scale. You need to be able to use it in a manner that is compute efficient, right? And you need to be able to do it in an amount of time that doesn't take weeks and weeks of developer time where you have like, oh, I got the model working on my laptop. Look at this. Let's productionize it. And they're like, I don't know what to do with this, right? It needs to be able to seamlessly transition from you prototyping on your laptop to this thing being available as an endpoint on the cloud for usage. All right, so let's talk about AutoGluon and why I think that we have covered and tackled all 7 of these key requirements to revolutionize how people use machine learning. So AutoGluon is an AutoML toolkit that democratizes machine learning. It automatically builds accurate models for image, text, time series, and tabular data in just 1 line of code. And it is open source and easy to install. Just install AutoGluon. Cool. So AutoGluon was used to teach over 15,000 Amazon software development engineers machine learning in 2022 via our internal Machine Learning University, or MLU, Day 1 ML course. This is basically a course that every software development engineer is assigned when they join the company. And so basically all software development engineers at Amazon have been taught how to use AutoGluon in just a single day. And basically that is their intro to machine learning. Is if you need to do machine learning, I don't know, just throw AutoML at it, see what happens. Maybe it's good enough. So AutoGluon is used in over 500 Amazon projects in production, as well as the backbone for multiple services within AWS, such as SageMaker Autopilot and Canvas. It is also adopted by over 100 companies, such as Intel, NVIDIA, IBM, Capcom, Mitsubishi. One example is Capcom, which in the most recent Street Fighter game, they use AutoGluon to figure out the player churn probabilities and predict when players are going to stop playing the game. So, again, as I mentioned, AutoGluon is fully open source. We work on Python 3.8 to 3.10. We have 4 million downloads and a lot of contributors, over 100 in fact. And you can find us on GitHub. So let's talk about what AutoGluon is and how it positions itself relative to the rest of the AutoML field. So AutoGluon came out in 2019, and prior work, generally speaking, focused on the cache problem, basically. Given a model and hyperparameter ranges, figure out the best combination of hyperparameters and models to get the strongest result possible. But AutoGluon is different in that it relies instead on strategies that win prediction contests on sites like Kaggle through thoughtful data preprocessing, model ensembling via multi-layer stacking, a greater emphasis on modern deep learning techniques, and boatloads of tricks and optimizations. So let's talk a little bit about hyperparameter tuning. And I know it's been a running joke that I hate hyperparameter tuning. I don't hate hyperparameter tuning. But so hyperparameter tuning is the idea that you have a model with a bunch of levers, right? And you can tweak the levers, and that changes your performance, right? And so if you can tweak the levers enough times and in the right ways, you can end up getting better performance, right? So that's great. However, each time you want to evaluate a given hyperparameter setting, you have to train the model, and so it requires many repeated model trainings to tweak the levers. Most of the models that you train are just end up being thrown away because they're suboptimal, and so it's, in a sense, wasted time from what optimally could have been done if you just knew the correct model from the get-go. And the more hyperparameter tuning you do, the more you end up overfitting on your data, and your validation score starts getting less representative. And so you can combat this by using more validation data, but then you're using less training data, and so your models are weaker. Or you could use cross-validation, but that again then takes much more time to train your models. And there are techniques in which you can try to mitigate this, like hyperband and Bayesian optimization, right? But AutoGluon decided to go a bit of a different route. And furthermore, hyperparameter tuning is less helpful when ensembling because having a good model individually doesn't necessarily mean that it's the best combination of models. Okay, so now let's talk about ensembles. Very simple example is a random forest. So a random forest is just a bunch of decision trees averaged together, suboptimal decision trees, in fact, averaged together. And decision tree, I'm not going to really explain it. I think you guys probably know what that is. So you can imagine that you have this kind of a data where you have x and y features, which are coordinates, and you want to predict the color of the dot. The lighter the color, the higher the value of a regression problem, right? And so what a decision tree would do is it would split it up by all these binary decisions, and then let's color that in. And so this is the prediction that the decision tree would make at any given point in this space. Now, this is obviously suboptimal because there are these harsh decision boundaries where the color changes rapidly from pixel to pixel. And here's a bunch of different randomized decision trees, right? Basically with suboptimal decision trees where you train on only a portion of the training data, stuff like that, like leave out features or whatever. But the magic comes when you average those together. And now you have a result that is stronger than any individual decision tree. In fact, it's stronger than the strongest decision tree. If you hyperparameter tune a decision tree forever, you wouldn't actually get a result that's stronger than the random forest. So there's something inherently stronger about ensembling here than hyperparameter tuning. So simple takeaways here is generally many models are better than few because when you average them together, you kind of are able to capture the strengths of each one and they can synergize with each other. Models that learn differently can boost accuracy even if they're worse in isolation. And hyperparameter tuning to find the best single model does not necessarily help find the best combination of models. All right, so who here has heard of the Netflix prize competition? So this is an infamous competition where the prize was $1 million, and you needed to create a model that beat Netflix's baseline algorithm by 10%. This turned out to take many years of people's work and scientific innovations to be able to do. And the end result was a very complicated combination of hundreds of machine learning models that was so complicated, Netflix didn't even use it. So in this sense, I would call this a monster because it is the most powerful thing that could have been achieved at the time, right? No one's holding back, it's $1 million. But it's just impossible to work with. It's too complicated. You try to have software development engineers who don't really know machine learning, and you give them this thing, and you say, okay, re-architect that and make it productionizable. And they're just not going. They're going to quit their job. They're going to sue you. You know. So, in that sense, it's a monster. And of course, there's Kaggle, competition data site, where again, whoever gets the best accuracy, RMSE, whatever, gets all the money, right, in these competitions. And so it started becoming the case where basically every competition was won by these very complicated combinations of hundreds of machine learning models and this technique called multi-layer stack ensembling, which basically wasn't in pretty much any research papers or anything. And it was just this black magic that people did in Kaggle, but was nowhere to be found in industry or anything like that because it was too complicated. So my question, and the question I pose for AutoGluon is, can we tame the monsters? So Can we make them reliably performant, stable, and sensible to countless different data sets? Can we assemble them in an appropriate manner without need for expert knowledge from the user? Can we train them in a reasonable amount of time on a wide variety of hardware? Enable flexibility to satisfy user constraints? And most importantly, hide the complexity behind an elegant API, going back to what I was talking about earlier, which is, what does it mean to be a complex solution? My definition of a complex solution is one that is difficult for the user to implement. But if you use complex techniques, but it's easy to use, I would call that a simple solution, an effective solution. AutoGluon strives to achieve these goals. AutoGluon strives to tame the monsters. Okay. So, how do we do this? Well, first of all, model variety. Take the absolute best of the open source community, slam it all together, and get the widest model variety possible. Take all the state-of-the-art algorithms, XGBoost, LightGBM, CatBoost, scikit-learn, grab stuff from Hugging Face, grab stuff from Tim, go and use the fast AI neural network model. Anything and everything to add diversity and strength to the ensemble. Then we use a technique called bagging. Bagging is when you train the same model across your data multiple times, basically doing different splits. Now, you can think of a random forest as an example of a bagged ensemble model. But here we do it in the sense of cross-validation. And we do this for a very particular reason that I'm going to show you in the next slide. But basically, we ensure that on all of the data that you have available to train, by the way, there's no such thing as a holdout validation set here. We don't use that. That every row of your data was validation at one point for at least one of your folds in your models to generate something called an out-of-fold prediction or prediction probability. Next up is stack ensembling. This is much more complicated than I can really explain in this talk. But to give an idea, basically, you can convert model prediction probabilities into features and use those features as things to train additional models on that improve your predictive accuracy. And you can repeat that process, and you can concatenate it with the original features, that you can use any model types you want at both the base layer and the stack layers. And so the layer L+1 stacker model uses layer L predictions as extra features. Now, how do you avoid overfitting in this case? This is the purpose of the out-of-fold predictions. Basically, you use the out-of-fold predictions as the features instead of using directly like the training data or holdout validation. If you want to talk more about this afterwards, if you're curious, just come up to me. So for simplicity, stacker model types are the same as the base model types in AutoGluon. Basically, we say, okay, if we have a strong set of models that are good at solving machine learning problems, basically, we've created another machine learning problem with additional features, so we're going to use those same types of models. And yeah, this is that nuanced thing, but let's not worry about that right now. But basically, this ends up working, and this is also what is done in Kaggle. But we basically automate it, so it does it out of the box. Okay, so that's it basically for like the very simple breakdown. Now there's a ton of nuanced stuff in terms of feature preprocessing and stuff like that, and how do we choose the default hyperparameters of the models. But what I just said is the high-level idea of the entire system. Okay. So to obtain the upcoming results, we did not hyperparameter tune. We, in fact, used the same hyperparameters for every problem. We used the near factory default hyperparameters for all models. And we trained using the same 3 lines of code for every problem. So from AutoGluon.tabular, import tabular predictor. Predictor equals tabular predictor. Specify the label column you want to predict with. Specify your training data. Specify the preset, such as best quality. And specify your time limit. How long do you want it to run for? Then it's going to do its magic. And then you just call predictor.predict and pass in your test data, and now you have your predictions. That is your solution. Whether you want to call what AutoGluon does complex or not, I would say this is pretty simple in terms of how the user interacts with it. Okay, so with that, in 2020, we released our original paper where we showcased that AutoGluon was able to get very strong results and achieve state-of-the-art in AutoML on the AutoML benchmark, as well as on 11 Kaggle competitions. And then in 2022, AutoML, they released a paper on the AutoML benchmark, now with 104 data sets, where they showed that AutoGluon was statistically significantly stronger than basically the other AutoML systems in this suite of data sets. In particular, in multi-class classification, where stack ensembling is very strong, AutoGluon gets particularly powerful results. So, furthermore, we took AutoGluon to Kaggle and machine hack competitions to see how it fared. We were able to get multiple top 1% and rank 1 solutions on historical competitions. To give an example of the AutoGroup competition, and to give an idea of the impact of this kind of a system, the competition, Auto, had over 3,500 teams compete on Kaggle. In 4 hours, AutoGluon achieved a score that took the best human team over 2 months to beat on Kaggle. And the solution that AutoGluon found in 4 hours got rank 14, which is Kaggle Gold, which is 1/5 of the way necessary to become a Kaggle Grandmaster. And so, yeah, again, did not compete during live competition in this scenario. But think of a tool, being able to use a tool like that. Not everyone is a Kaggle Grandmaster, right? People sometimes just need something to get the job done. And by having a general tool that's able to work out of the box and get good results can dramatically improve the rate at which people can deliver impactful features in practice. In terms of stability and robustness, AutoGluon is very stable. We've spent a lot of time ensuring that our memory estimates when we go to train models works well. We basically calculate, given the data, what is the memory expectation, and then when we do parallel training, we will limit the number of parallel jobs based off of the memory estimate. We will do graceful degradation of the system in case models start failing. Right, and so this is all to move towards 100% success rate in these kinds of tasks to ensure that when you go to use an AutoML system, it works, right? Because one of the biggest reasons why someone wouldn't use an AutoML system is if it doesn't work, because then who cares how good it is if you can't get it working. So this is a slide of basically the improvements over time of AutoGluon, both at inference speed and accuracy. So the y-axis here is the basically the normalized score across the AutoML benchmark, and the x-axis is the inference speed, basically going further to the left is faster. And with the infer limit setting of AutoGluon, you can dynamically change how fast inference AutoGluon has to basically have a trade-off between inference speed and accuracy over time, or basically by just a single hyperparameter. And we can see that as time goes on, we're both improving AutoGluon's accuracy as well as its inference speed. Yeah. And the other thing is that we're able to get quite fast inference speed such that we can basically match the inference speed of, say, an XGBoost model, but with a lot of performance improvement. So, question is, we talked about historical competitions, but can AutoML win a live Kaggle competition? So, in this competition that happened earlier this year, a Kaggle Grandmaster ended up using AutoGluon and winning a Kaggle competition, in fact. And this was quite interesting. One of the top Kaggle Grandmasters, Devastator, mentioned that he believes that it's the first time that's ever happened. It's very interesting. One of the things to take away here is that it wasn't AutoGluon on its own. It was custom feature engineering, hand done by the Kaggler, then fed into AutoGluon, right? And so this goes back to the idea that feature preprocessing is very important, right? But as the idea being that AutoML should be able to enhance your capabilities, right? If you know how to do feature engineering, then you should then put that into an AutoML system, not just like throw away AutoML and go to XGBoost or whatever, right? It's the idea that whenever you need the model aspect, you loop back to using AutoML as a piece of the toolkit. And so I tracked basically over the first quarter of this year, and AutoGluon was used in these 5 competitions to get pretty strong results, which I think is a good indicator basically that AutoML is picking up traction within the competition community, which I think then showcases basically the effectiveness in real-world scenarios. Okay, so with that, let's go to beyond just tabular data and talk about what AutoGluon is doing in both the multimodal and time series domains. So,
hello? Could you turn on the mic? 1, 2. Okay, let's try this one. I think this is okay. So I'll just go this way. Thank you, Nick. So as we have just seen, AutoGluon can achieve quite impressive results when it comes to tabular data, when we essentially have numerical attributes or categorical attributes. But of course, as all we know, machine learning problems often come in very different flavors, and we often have very different problem types that are not just all about tabular data. 2 very common examples are images and text that we often have to deal with. And these can be problems that only involve one of these data types. For example, image classification, such as ImageNet challenge, maybe something like sentiment analysis for text. But even more importantly, we often have problems where we have combinations of all these different data modalities that we call multimodal problems. To give one example of such a multimodal problem, we can look at the problem of problem of product matching that Amazon has to deal with quite frequently. So Amazon has a huge catalog of products available on the website, and for each of these products, we have different attributes. We have, of course, the title of the product, which is text. We have pictures that are images, and we also have a lot of other features, such as maybe price, numerical attribute, or categorical features for the different model types. And then the question that often needs to be asked is whether a certain product is a duplicate of another product. So let's say when some seller comes to the platform and wants to sell a new product, they have to know, like Amazon needs to determine if this product already exists in the catalog, because we don't want to have like many copies of the same product repeated in the catalog. So this essentially is a binary classification problem, but with this unique twist of having lots of different features coming from different modalities that somehow need to be all combined together. And AutoGluon also provides a way to solve such problems. Well, you can say if we work with data like images or text, we should just use foundation models, of which there exist many, of course. But then there are still many important questions that need to be answered before we can put such a model into production. So the first question is, of course, which model should we choose? We can go to Hugging Face to download the best state-of-the-art pre-trained foundation models for images or text, but there are 300,000 such models as of last week, which is quite a large number. So how do we know what is the best one to choose? And maybe different models require different data preprocessing. They all need to be used in different ways. So how do we know which models we should use? The other question is, of course, how to fine-tune these models, because not all of them work perfectly well in the zero-shot setting. And we often have to do some kind of fine-tuning for our specific problem to make sure that we get the best possible results. And finally, as we saw in the previous example, multimodal data such as images and text is often combined with tabular attributes, such as numeric. Oops. Thank you. It's often combined with also tabular data. So multimodal data like images and text is often combined with tabular attributes like that are numerical or categorical. And then there was a question, how can we combine the foundation models with the special data? Can we somehow combine the tabular models with the foundation models to solve these tasks at hand? So the first step to dealing with such tasks would have to somehow put everything together into the data. And actually, we can just do this with the pandas data frame with slightly extended definitions of what the data is. For images, we can just have paths to the images. For text, we can just store directly in the pandas data frame. And then once we have the data in such a format, we can throw it into AutoGluon and perform our different tasks involving multimodal data. So the idea here is also very simple. So it's the same 3 lines of code API that we have seen before. But now this allows you to take the data consisting of different data modalities and perform the tasks. And under the hood, this predictor uses all the different foundation models provided by Hugging Face or Torch Image Library or MMDet or the clip embeddings, combines them together and performs the different tasks. Unlike the tabular task where we can determine what the problem type is, here we have a much bigger variety of different tasks to deal with. Of course, there are the simple things like classification and regression, where we might be interested in classifying text or images or their combination, or doing regression where we have to predict some continuous target. But there are also some more sophisticated versions. For example, named entity recognition in text. When we have images, you might be interested in detecting objects in the image. And there are also different matching problems that we can encounter. For example, where we want to somehow correlate different image or text prompts with each other, and we want to determine whether they correspond to the same entity or not. And this example of doing product matching would be one such instance of multimodal matching, where we have to figure out whether different objects correspond to the same data. And the nice thing about AutoGluon is that it takes care of many of these questions that we have seen before for the user. So let's say if next week a new cool foundation model comes out, which now provides even better embeddings for text or images, AutoGluon with the same 3-line API would still be able to provide, will incorporate this model, and the end user would not have to change the API of what that they have to invoke in their code to see the result. So in the end, it's the same 3 lines of code, but let's say when the new version comes out, we now have all the new models, maybe some new state-of-the-art solutions, maybe some additional efficient parameter fine-tuning techniques that are all now incorporated and wrapped under the same single code to the fit method. And the way the predictor actually works under the hood is it combines passes the different types of data, the different modalities through different foundation models to obtain the embeddings for them. So for example, for images, we use TIM and detection. For text data, we use transformers from Hugging Face. For the combinations, we can get the clip embeddings to get text image embeddings. And finally, for tabular data, we can use things such as FT transformer. Then the embeddings from all these different models can be combined together. And there are different strategies for how they can be fused. We can essentially either stack the embeddings and then apply something like a tabular classifier on top, or we can also combine the embeddings and then have another several layers of transformers that would be able to process the different embeddings and capture the interaction between them. And these strategies are known as early or late fusion in multimodal data. And finally, all of these different features obtained by different foundation models can also be combined with tabular algorithms, getting the advantages of both worlds. So we have both the foundation models to extract the features from images or text, and we have the tabular models like LightGBM, XGBoost, taking advantages of this information and being able to achieve the strong empirical results on tasks that we care about. The next kind of data modality that I want to talk about today is time series forecasting, which is something else supported in AutoGluon. In general, as many of the talks today already mentioned, time series forecasting is really everywhere, and whenever we have any observations that are collected over time, we are essentially dealing with a time series problem. And usually, the question that we want to ask is, given some observations that we have seen in the past, what will happen in the future? For example, if we have seen, let's say we are, again, back to our example, we are some online retailer, we are selling different products online, and we want to predict how many sales of certain product will happen in the future so that we can properly plan our inventory and make sure that we have enough items in stock to satisfy the demand. In this case, we can represent our historical sales data as a time series that we measure maybe for each day. We know how many items we sold. And then the question that we ask is what the sales will look like in the next 2-week forecast horizon. The way we want to answer these questions is not just a regression task where we want to get a single prediction for each future time step. So I don't just want the model to say we will sell 100 units tomorrow, because this doesn't capture the uncertainty that is really important for making the decisions. We often want to have a probabilistic forecast, which includes the range of possible outcomes. So for example, the model might say that there is a 90% chance that the number of units sold tomorrow will be between 90 and 150. And this would be a more useful information for us to do the decision making so that we can, in our planning, we can understand what the uncertainty involved is. This kind of forecast is known as a quantile forecast or probabilistic forecast, and this is what most practical applications of time series forecasting require. Of course, this very simple example where we just have a single product that we have observed in the past and we want to predict its sales in the future is quite simplistic. And very often we have to deal with much more complex tasks where a lot of other information is available. So the first thing is just the number of time series. So we often don't just have to forecast sales for a single product. We want to forecast sales for multiple products, maybe tens or hundreds of thousands of products in our catalog. So we have to do prediction for multiple time series at the same time. The next type of information that we often have available are so-called covariates, which is essentially any information, any additional information beyond just the historical values of the time series. For example, for the sales, something that might be important are holiday features that indicate which future days are holidays, maybe some promotions that we apply to our data, or sales of related items. So let's say you want to predict the sales of some clothes, like clothes in one category, maybe sales in a different category could be useful. And another type of information besides these covariates that are essentially other time series related in capturing some information that is necessary for forecasting. We also might have access to metadata, which is essentially some static attribute that just doesn't change over time, but is still relevant for forecasting. So for example, back to the example with sales prediction, maybe a brand of the item that you want to predict, or its price, or location of the store where the item is sold. They can all be relevant for time series forecasting. And by combining all this, AutoGluon can actually solve forecasting problems that contain all this different information consisting of multiple time series with different covariates and metadata. And the API here is, again, quite simple, where we just have 3 or 4 lines of code, depending on how you look at it, where we can provide our data as a CSV file or any other format that is available to you, create a predictor object, define our forecasting task. For example, we can say how many steps into the future we want to predict. We want to determine which quantiles we are interested in, or maybe which column, or like which target time series we are trying to predict. And then we call fit and predict, same as we have seen before with tabular and multimodal. Of course, the most interesting part here is what happens inside the fit method and how AutoGluon is able to generate forecasts for time series data. So in general, time series forecasting is quite an old problem, and there exist many different approaches, or even families of approaches. And historically, people often like to prefer one category of approaches to others. For example, if you look at statisticians, they will often say, well, statistical or econometric models is all you need, and all this new fancy deep learning stuff is just a waste of time. It doesn't work. Maybe people more in the machine learning community, they prefer to just use LSTMs or some deep neural networks without really considering statistical baselines. Or in technical computations, people just use stuff like LightGBM or XGBoost to win the computations. But in AutoGluon, we take the approach of combining everything together, all the different approaches, without really giving preferences to one of them, and then running the ensemble on all these diverse models to determine what the best combination of the models is. And as we'll see in a few slides, this ensembling is actually the key component here. So it's not about any individual models used by AutoGluon, but it's more about ensembling of the forecasting models, which allows us to get accurate probabilistic forecasts. So the first class of models, the statistical models, maybe something that you learned about in your statistics class, are these very simple things that, like very simple models that capture some simple patterns in the data. For example, we often have stuff like trend or seasonality in the data, where we have some repeating patterns. Maybe if we have electricity consumption, then very often we have peak demand in the middle of the day, and then there's very little demand in the night. And these kind of cyclic patterns, such as seasonality, or maybe trends where time series slowly grow or decline over time, are well captured by these simple models. Some examples of these models are ARIMA, ETS, also known as exponential smoothing or theta. And another key feature of these models is that they are so-called local models, which means that we fit a single model for each individual time series in the data set. So in our demand planning example, if you want to predict sales for multiple, maybe 100 products, it means we'd have to fit 100 time series models, like one model per each time series, that would capture the specific patterns present in this individual time series. The second class of models that we consider in AutoGluon are deep learning models that are much more flexible, and very importantly, like the main distinction is that they are global models, which means that we don't just fit a separate model for each time series, but rather have one global model that learns from all the time series in the data sets, in the data set. So it would learn on all the sales for all the different products to combine that information, but still do the prediction individually at prediction time. These models are much more flexible and often don't make these strong parametric assumptions, such as the statistical models, so they can capture some really complex patterns without user really specifying them in advance. They're also really good at capturing the covariates, all this additional information, because we can easily, for example, handle categorical data with embeddings for all the other types of covariates. They're also very easy just to add as input to the neural network, and then if they're useful, they end up being picked up by the model. And some examples of these algorithms are DPR, temporal fusion transformer, or PatchTST. And finally, the other class of models that we consider are tabular forecasting models that essentially work by converting the time series forecasting problem into a regression task, or maybe a quantile regression task. So here we see, as an example, this time series consisting of 6 observations, and that are, of course, sequential. We can obtain lag features from this time series, and therefore turn this, convert this one training sample of a time series into a training feature matrix X and the training target labels Y. And as you see at each time step, we're essentially trying to predict the next observation of the time series by considering all the previous observations as additional features. And once we convert the model into this task, we can just use our favorite regression algorithm or quantile regression algorithm. And that will then, by reverting this process, by essentially generating the predictions one step at a time and feeding them back into the model, we can now generate a forecast for the time series. And luckily for us, we didn't have to implement or write all these methods from scratch, because we had AutoGluon Tabular to rely on that already has implementations of all the most popular regression and quantile regression methods that we could just use as components to define such tabular forecasting models. Finally, in my opinion, the most interesting part, or the thing that actually makes everything work, is the ensembling step, where we combine the predictions from different models. And the idea is, I mean, in essence, it's very similar to what we have seen before, but in AutoGluon Tabular, because we have tabular data which has independent, or IID, rows in the data matrix, we could just do bagging, which is a very simple and very powerful technique. But for time series data, this bagging approach doesn't work anymore. And the problem is that we cannot just shuffle the entries in the time series data and treat them as independent from each other. Of course, there is this strong sequential dependency that is the key feature of time series. Therefore, to do validation properly on time series, we have to generate these validation splits in a rolling window fashion, where we just remove the final part of the time series and always reduce the amount of training data available. And by repeating this cross-validation procedure, but now in this time series flavor, we again have a bunch of validation sets, shown here in green, that we can use to evaluate the performance of the individual component models in this out-of-fold fashion. So essentially, the algorithm is simple. For each model included in the model zoo, we train it using different folds of the cross-validation procedure. We evaluate its performance on the validation set, shown here in green, and we store these predictions separately for each individual model. And now, once we have these predictions for the individual models, we can fit a weighted ensemble on top by essentially taking a linear combination of the individual models that maximizes the score on this validation set. So the algorithm is very simple. It's something from a paper by Caruana et al. From 2004, where essentially we just do greedy stepwise selection by finding the best weighted combination of the models that would maximize the score on our validation set. And then essentially the final ensemble here is not the complex stack ensemble model, it's just a simple weighted ensemble that combines predictions of individual models in a linear way. And this can also apply to probabilistic forecasts. So if each model generates a quantile forecast, we again just can represent this quantile forecast as a vector. So for example, the P90, so the prediction for the 90th quantile is just a vector that each model outputs. And then for all the quantiles, we just multiply them by this weight, take the weighted average, and this is our probabilistic forecast. So in a way, it's something very simple, but also to initially seem like quite counterintuitive that such a simple thing also works for probabilistic forecasts and actually achieves really good results, as we'll see in a few moments. So the first thing that I want to look at is our benchmarking results here for point forecast, where we compared AutoGluon time series with lots of different established frameworks that include both simple statistical models like ETS or REMA that we've seen so far, also some deep learning models that are extremely popular in the industry, such as DeepAR or Temporal Fusion Transformer, and even one AutoML framework called AutoPyTorch that also can do time series forecasting. The way we evaluated the model is by taking 29 benchmark data sets, evaluating AutoGluon and all the other frameworks on all of them, and then looking at the accuracy of the point forecast using the mean absolute scaled error metric, and seeing how well each of these methods individually does against AutoGluon. And we've seen that there is quite a large gap between the performance of AutoGluon and many other benchmarking methods. And I think one explanation for this is that AutoML for time series is a relatively underexplored topic, and there don't exist that many AutoML frameworks considering this type of problem. So there is even with some simple approaches like weighted ensemble, we can actually get really good results in here. So we see that we got the best results on 19 data sets, and the average rank is consistently lower than for the other models. And this last here also tells us an interesting story that it's not just AutoGluon is better by a tiny margin, and that's why it has a better rank, but rather the rescaled error is also much lower. So the gap between AutoGluon and the competitors is quite large. Of course, the next question that we want to ask is AutoML systems performance is good, but there's another important component, which is the runtime. So we don't want to have something that takes forever to train, and we want to get the predictions quickly. And here we see that we set the time limit for 4 hours for all the models, but actually AutoGluon was able to get the results consistently under the 1 hour mark for all but 2 data sets. It was able to finish training in 1 hour. And another very interesting thing is that these simple local models like ARIMA, Theta, or a combination of these statistical models that we call stat ensemble here, they often took an extremely long time to train. And this is another interesting finding for us, that actually these models, they can be extremely slow in their implementation provided by different libraries. But if you do some tricks and find ways to stop their training to respect the time limit, as we do in AutoGluon, they can actually be quite useful and reliable. But in general, if you have lots of data, they might not be the best approach. And even deep learning models, where you can very easily control how long they train, might be faster than the statistical models applied to extremely large data sets. And finally, to what I think is the most interesting part here is we look at, OK, so why does AutoGluon actually work quite well? How does it manage to beat all the baselines? And we found that ensembling is, in fact, the key component in here. So the way we did this is we tried different ablations for AutoGluon where we disabled various sets of things in the model. So here we see 3 types of ablations where we removed all the statistical models from our model zoo, where we removed all the tabular models from the model zoo, and where we removed all the deep learning models from the model zoo. And as you see, even if we removed all these individual models, the performance actually doesn't drop that much, and it doesn't change. So this essentially means that there is no single model that works extremely well, and that's why AutoGluon is good, but it's really the ensembling that is the key component that helps here. And the worst thing that we can do to the predictor, the worst ablation, would be to just disable the ensemble, in which case we just select the single best model that has the best validation score, and this would lead to a huge performance drop, which essentially shows that for time series forecasting, ensembling really is the key component that allows us to get accurate results. And another interesting finding is that even if we move the time limit very aggressively, like if we reduce it to 1 hour or 10 minutes, we can still get really good competitive results, even under these very strong budgets. Thank you. Now Nick will take over with a hands-on tutorial where we try out AutoGluon Tabular.
All right. Thanks so much. Testing, testing. All right, sounds good. Yeah, so thank you, Alexander, for the great introduction to AutoGluon multimodal and AutoGluon time series, right? All of these modules are like in the overall AutoGluon ecosystem. I'm gonna go over the hands-on tutorials. I'll be doing it here. If you want to do it yourself, feel free to follow along or basically do it offline separately. We're gonna keep it fairly straightforward. I'm gonna go here. So as I mentioned before, I ran this first cell so that AutoGluon is installed already by the time I start this. And so let's give it a go, shall we? So first of all, when using AutoGluon, you gotta import it. Sounds good, let's do that. Hopefully, you know, this thing didn't time out on me while I was waiting here, but we'll find out very soon. It's looking good. And then, so here we have a data set. This is the adult income data set. And we're going to subsample it just for the sake of making this pretty quick. And then let's take a look at this data. So here you go. So this isn't some clean numeric only data that is all numbers and no missing values. This is kind of nasty, right? You have raw text going on here that you're going to need to convert, like treat as categoricals or something. We have binary features and mixed with numerical, right? And what we're going to try to predict here is the class, which is binary classification on if someone made greater than or less than $50,000 in a year. So here we go. Yep, basically it's binary classification. So basically, all you need to do is, again, specify the label, which is, class. Specify your save path if you want. We can just create a generic one if we don't have it, so that's fine. And then just pass your training data, and let's see what happens. So AutoGluon is going to tell you a whole bunch of stuff as it's running. For example, it is going to tell you the version that you ran it in. It's going to tell you the Python version, the operating system, the platform version of your machine, how much disk space you have available. The reason we do these things is, one, for the user's convenience, but two, for my sanity when they open a GitHub issue and say that it's not working. Now I can show me the logs, and then all of this beautiful information will be there to make my life so much easier. And so it'll tell you, okay, how many rows of data, how many columns, what's the label column, and then we go into data preprocessing. So remember, models like numbers. They don't like words and texts and stuff like this. So how do you convert that data into something that'll actually work? First thing, what problem are we even trying to solve? We never said it was a binary classification problem, but AutoGluon automatically detects this based off of looking at the label column. So it says, oh, there's only 2 unique values. This is binary classification. And we have similar logic for multi-class and for regression. So it's just one thing that you could probably infer in almost all cases correctly. So why not just do it, make life easier for the practitioner? Now, we also tell people which class we chose as the positive class versus the negative class. This is important for a variety of things. The user can also specify which one they want to be the positive in case they're doing something like F1 score or whatever, right? So we say specifically, we note in this case that, hey, we made a decision that's opinionated. If we're wrong, please run it again and specify this exact thing in terms of how to do it your way. So now we move on to the feature generator. So we first basically do all these different types of stages of feature preprocessing. We detect the types of all the features. This is something we could definitely do better. Currently, it's quite simple. We basically just do whatever Pandas does to figure it out, and we just kind of trust that for the most part. We have some custom logic with the text as well that works pretty well. And then we do filling of missing values. Now note, we don't actually fill most missing values here. We actually keep the missing values throughout the preprocessing in general in most cases, because oftentimes missingness is not at random in practice, and therefore you should be able to use this as a feature that is actually indicative. And so you actually don't want to impute missing values in all cases. A lot of times you want to keep those around. But we specifically have a fill-in for an edge case where a feature didn't have missing values originally, and it was an integer feature. And then at test time, it's now a float type because there's a missing value. And you literally can't represent it as an integer in pandas with missing values, and so you'll crash. So that's a fun thing you'll run into eventually if you make an AutoML system. And then we basically do category feature generations. Basically, we just do label encoding initially, and then we let the downstream models choose their particular type in which they want to represent the categorical features, but this is mostly for memory optimization. We drop unique features. So basically, if a feature has no predictive value in the sense that it has different unique values for every row and it's not like a float, then we can drop it safely because we know that there's no information to be gained. We can also drop duplicate features. So if two features have the same value for everything, you can drop and only keep one of them. And then we also do things like detect Boolean features automatically, right? So we detected that this is a Boolean feature because there's only, oh, I've ruined everything. Never mind. Right, and so we automatically detect this, and then for certain models, we will treat that feature differently. And notice also, originally the data was 1.17 megabytes, right? And then after preprocessing, it is 0.12 megabytes. So we also optimize the data types of the data to make it so that we can train models faster and with lower memory overhead. Okay, and that's the data preprocessing. It took 0.45 seconds, right? Pretty straightforward. And then we optimize the hell out of this for inference so that it's very, very fast. Okay, so now next up, so because we didn't specify an evaluation metric, it just defaults to the default one, which is accuracy, but you can specify whatever metric you want or a custom metric. In this case, we're not doing multi-layer stacking because this is just a simple tutorial that's quick. So we automatically do holdout. Here we say the exact hyperparameters and list of models that we're going to be training. Note, in a lot of cases, this is basically the defaults. When it's like this is like basically default hyperparameters at cap boost, with a little bit of caveat in the sense that we have things like early stopping, and we set the iterations to basically infinity for most of these things. But like very close to defaults. So we don't like have any super fancy hyperparameters particularly. And then we just fit these models and we keep track of their accuracy and training time and validation score, right? Cool, pretty simple, straightforward stuff. And then finally we create a weighted ensemble, and then that just ensembles it together to get a better result. We use Caruana et al. For the ensembling method, ensemble selection. Now, okay. Cool, that's our training. Now, here's our test data, right? Same deal, just no label there, and then, well, you know, either you can use the predictor that's already in memory, or you can load it from disk, and you can call it predictor.predict and evaluate, and there you go. That's like the bare minimum you need, really, to actually, you know, do something. You know, like now that you have something that can predict and predict Bravo and all that stuff, you know, you can move on and, you know, solve a business problem with this, right? You can also do a leaderboard. This shows you the accuracy of every single model that we trained, as well as statistics like the inference time. Yeah, so like the test score, validation score, inference time, how long did it take to fit. You can even specify extra information here, and you can then get how much memory does it take up, how much disk space, what's its hyperparameters, all this stuff, what models does it connect to. And you can also choose any of these models when you call .predict. You can specify model equals, and so you can use any one of these models you want, and then you can also do an optimization for deployment where it deletes every model except the ones that you care about, and it basically creates a minimal disk and memory version of the predictor for you to deploy with. So yeah, that's basically like the real simple initial stuff here. But like I could show you some other stuff real quick here, like for example, predictor.featureImportance. which uses permutation shuffled feature importance, which is relatively quick to do, and it's a black box technique, and this gets you quite accurate feature importance values for the overall predictor, and it works with the ensemble as well. Now, I don't know how long this is going to end up taking here, because I kind of increased the number of samples just for the fun of it for this, and now I'm kind of regretting it. But, you know, we'll see. This is just one example of, you know, using AutoGluon, but it's a very similar process for multimodal and for time series. And we have a bunch of functionality. Oh, here we go. So yeah, so now we have the feature importance of all your features. This value here is actually the amount that accuracy will drop if you remove the feature. What this value actually means is if you randomly shuffle the values of this feature among all of the rows of data that you have, this is how much your accuracy will drop, which is a good proxy for how much your accuracy will drop if you actually remove the feature, while being much faster to compute. And then we also have things like p-value and standard deviation to give certainty in terms of how certain are we that this is actually important. And then we also have automatic feature pruning logic that's available if you enable it, and it'll probably be enabled by default in 1.0, that iteratively does feature pruning based off of this method and basically removing the least impactful features, and you can actually increase accuracy doing this. We'll also increase it, or also like speeding up inference and all of that good stuff. Yeah, there's a lot more here, but I don't want to take up too much time. So that's going to be that for the hands-on section, but feel free, if you go to our website, basically the nice thing about our website is that, so this is auto.gluon.ai, is that all of our tutorials have a open in Colab button, and you can just open all of them in Colab and just run them and do whatever you want. And so if you want to talk about running tabular plus text plus image, you can open in Colab and then select a GPU instance and then just run that. Or if you want to, you know, do time series, quick start, or multimodal, right? We have like a lot of tutorials. Some might say too many, but yeah. So that's that. So now that we have trained our model, right? Trained it on your laptop or whatever you want. Basically, how do you end up actually using this, right, if you're in industry? Because really what you want is just a machine that has this model and you're able to query that machine and it just returns you predictions on new data, right? You can't be like hosting your model on your laptop. That wouldn't be any fun, trust me. So how do we make this process easy, right? Well, we created something called AutoGluon.cloud. And so here is all the logic you need to be able to train on the cloud. From AutoGluon.cloud, import tabular cloud predictor. Specify the label column, specify the training data, the time limit, literally the exact same things you needed to specify before, and just specify basically which S3 bucket or like location you want the output to be saved to, and then call fit, and just specify the arguments, the input arguments and the fit arguments that you would have sent to tabular. And it is going to then launch an EC2 instance or like a cloud instance and train your model. Okay, now once you've done that, how about deploying it? All right, cloud predictor.deploy. Now it's on the cloud. There's an instance that is running that has it hosted. And if you want to predict on new data, such as test CSV, you just say result equals cloud predictor.predict real-time test.csv. Then you get your results. And if you want to clean up that instance, you call cloud predictor.cleanup deployment. If you want to predict on a batch, cloud predictor.predict test.csv, and that just spins up an instance, predicts for you, returns it to you, shuts down the instance. And the fun thing is that you can do this, you can train on your laptop, and then convert this to a cloud predictor, and then host it in less than 5 lines of code. You can train in the cloud, download it to your local machine, load it, and predict on it locally, right? So you can do prototyping on your laptop, find, OK, this is the model that I really like, and then say, OK, cloud predictor upload that artifact to the cloud directly, and then 3 lines of code, you have it deployed. And so this dramatically simplifies the basically the hurdle that a lot of teams face, which is, I don't know how to productionize this, right? We make it as simple as possible. So there's like auto scaling and all that stuff, selection of GPU instance. We just handle that automatically. But we also provide the customization ability for you to specify things as well. And so this is what many teams internally at Amazon and also external companies use in order to basically get things going to solve their problems. OK, so real quick before I go into this, I'm actually going to showcase a quick video from an example. So this is a Amazon service that actually uses AutoGluon as their backend. And so they're able to then focus on maximizing the quality of the user experience and just know that all of the ML stuff that they need to do is just kind of constantly being proved on and worked on and is open source and all that.
Many companies want to use machine learning to better predict business outcomes. Amazon SageMaker Canvas provides a visual drag-and-drop user interface that helps business analysts create accurate ML predictions, all without writing any code or needing ML expertise. You can browse and access disparate data sources and quickly combine data sets to prepare data for your model. It enables you to cleanse and analyze data to get early feedback on the estimated model accuracy and to identify the most impactful columns in your training data set, ultimately improving your predictions quality. By automatically building, training, and tuning several model candidates, Amazon SageMaker Canvas identifies the best predictive model based on your data to help draw powerful insights. With built-in reports and metrics, you're able to further explain, review, and interpret the model's performance. You can also share your models with data scientists using Amazon SageMaker Studio to review and collaborate. Create accurate machine learning predictions on your own by getting started with Amazon SageMaker Canvas.
But anyways, right, so they were able to, create this service and focus on the user accessibility and that interface without needing to worry about the machine learning because they could use AutoGluon basically as their backend to do all those things. And they just call the APIs and just build on top of it, right? That's what multiple AWS SageMaker services actually do in the backend. So now let's talk about those 7 steps to an AutoML revolution and what that means for upcoming AutoGluon version 1.0. What have we achieved or basically want to achieve by that time? So ease of use and widely available. Just pip install AutoGluon. 3 lines of code end to end. Python 3.8 to 3.11 supported, also on Linux, Windows, and macOS, and with ARM. We will support tabular, text, vision, and time series modalities. Strong performance. State-of-the-art AutoML performance used by Kaggle grandmasters to win Kaggle competitions. Fast inference speed, capable of 10,000 plus rows per second throughput while retaining state-of-the-art performance, and capable of less than 10 milliseconds end-to-end inference latency. Stable and reliable. We made further improvements after that paper that said that we were 99.86% success rate on the AutoML benchmark, and we have since fixed our memory estimates in certain edge cases. We are now 100% on the AutoML benchmark, and we work with our partnering teams that use us in production in Amazon to ensure that we work in as many situations as possible and scale. We also offer an official security certified Docker container, which basically is constantly scanned for vulnerabilities that can occur due to security issues, and we patch that on a monthly basis, making sure that there is a golden standard version of AutoGluon pre-installed in a Docker container available for use. And this is how people use AutoGluon in production. And the back end of AutoGluon Cloud, the thing that gets spun up, is this security certified Docker container that then is able to train and infer with AutoGluon. And we also have continuous and active development. We have a team full-time at AWS of 12 people working on the AutoGluon project. And additionally, we have a variety of external contributors and partner teams that help us ensure that we continue to stay state-of-the-art and on top of any new developments. We're customizable. We're open source Apache 2.0. Basically, we're very open to people editing and tinkering with our stuff to make sure that it satisfies their needs. We have a modular design, AutoGluon.tabular, .time series, .multimodal. All of these are independent modules that can be installed separately and have minimal and have optional dependencies associated with them so that you can ensure that you can have a minimal install experience to suit your needs. And additionally, we have custom model support. If you have a model that you want that isn't in AutoGluon, you can easily wrap that model in our abstract model code. We have a tutorial for that, and basically add it to the system. It's interpretable, at least in the sense of what I would consider to be useful interpretability, such as we have the feature importance that I showcased. We also have Shapley value support. We have an entire module dedicated to this called AutoGluon.eda, which is basically automated exploratory data analysis that we're working on. And we have extensive logging and documentation as well as tutorials. We are deployable. We've created AutoGluon.cloud to make it so that you can go to the cloud and deploy and train just a couple lines of code. This is the current state of the system and what we are hoping to be a full, complete package for AutoGluon version 1.0. But I think that there's one thing missing. And this is something that I think will truly make AutoGluon be what I would be happy to call 1.0. The 8th step, ease of contribution. You see, AutoML is complicated. There's a lot going on, and there's a lot of nuance involved in determining how do you improve an AutoML system. If somebody wants to contribute, they're eager, and they have an idea, and they open a pull request, how is that experience for them prior to that thing getting merged? Are they feeling like they are a part of a community that is responsive to them, that has built the tools necessary for them to be able to provide a good contribution in the first place? Are we able to expediently respond to them and give them suggestions that are useful, right? So I want to make sure that AutoGluon is something that goes beyond the core development team. I want to create a community. I want to make it so that the AutoML community can find a place in which they can test ideas that synergistically can be combined with everything we've already done in AutoGluon to advance the state of the art, instead of people siloing themselves into these individual projects that then never see the light of production, basically. So how do we ensure an AutoML system stays relevant in a rapidly advancing field? How do we manage complexity and system design? How do we tell if one version of the system is better than another? What is our acceptance criteria, and how long does it take to figure it out? How do we encourage and enable outside contributors to participate? So let's talk about the first thing that we're doing in that regard, AutoGluon.bench. The goal is quite simple. Determine if A is better than B as quickly and accurately as possible, where A is literally any change anyone can make to the system, and B is the current mainline state of the system. How do we ensure that a given change, we know if it's an improvement or not? If yes, accept the contribution. That's it, right? If it's better, if we trust this metric, then throw opinions to the side, just accept it. We have improved the state of the system. If no, provide sufficient details to explain why no, and maybe what are the gaps needed to make it become yes. Examples. LightGBM releases a new version. Should we upgrade? The general wisdom would be yes, you would upgrade. But what if they have performance degradation on certain data sets and their memory usage starts being twice X what it used to be in large data sets, right? What if it breaks in certain scenarios, right? So it's not actually trivial. And then what if a user wants to contribute a custom model? Should we add it, right? So what is AutoGluon.bench? It wraps AutoML benchmark to automate the execution and monitoring of large-scale benchmarks. It has built-in evaluation logic to compute various performance statistics such as win rate, inference speed, Pareto frontiers, etc. And it's able to mix and match historical benchmark runs to compare numerous versions of the system and track degradations over time. So that is basically a system where we're able to spin up hundreds or thousands of instances with basically one line of code and aggregate all the results together at the end, make sure that there were no failures, and to automatically retry things and Dockerize everything of all the systems that are being ran, and then aggregate all the results together and then run evaluation logic that is able to tell us if A is better than B. Next, AutoGluon dashboard. So given that you have all these statistics and you did this run, it integrates with AutoGluon Bench to provide a front-end web interface for analyzing benchmark results. It's integrated with GitHub, or at least it will be very soon, and which allows us to comment directly in a GitHub pull request to both launch AutoGluon Bench on that particular pull request and compare it with mainline AutoGluon, and create a dashboard of the results, and it will respond in the GitHub issue that, hey, we have finished the benchmark, here is the dashboard of the results, please take a look, right? And we have a demo. So you can try this out if you'd like. It's also in the Discord. I'm going to give it a quick whirl. Basically, it runs on Pyodide, which is an in-browser Python environment. It's very neat. If you haven't tried making something in Pyodide, it's pretty awesome. So here's what it is. And this was created by an intern recently, which is fantastic. So this is an example, the AutoML Benchmark 2022 results. Just to give like a baseline idea of what this is, we're currently working on actually productionizing this and making it so that it's integrated into GitHub. Everything that's going to be something we're doing for 1.0. But you can see a breakdown for every single data set. You can take a look at how all the frameworks compare. You can look at the loss rescaled, training times, inference times, all these statistics aggregated across everything. You can look at, per data set comparisons, rank comparisons, error counts. It'll list all the data sets that there were errors. We're also planning to make it so that the error logs are also going to be something where if you click a particular data set, it's going to go straight to the error logs, and then you can look directly at what happened in that particular failure. We also have box plot of framework performance. And what you might notice here is that this is starting to look a hell of a lot like what you'd have in figures for a paper. And that's because I want in my next paper to literally just have this and never have to mess around with writing all these plots and all this stuff, right? I want a singular, standardized way to tell, is something better than something else, in what ways, and basically provide as much of that kind of information in one place as possible. And then, we also have like Pareto frontier plots of like training time versus or accuracy, and like infer time and accuracy, right? And we are even playing around with EC2 hardware metrics. So for example, keeping track of CPU utilization, memory utilization, disk usage over time of every single run, so we can tell basically, are we running high on memory or are we using a lot of disk, right? Just as much information as we can. And what we want to do is provide this to every contributor that tries to contribute to AutoGluon so that they feel included, they feel like they are informed as to the status of their contribution and what they need to do to make it to where it is something that we can accept. And this is a big focus of 1.0, is to make things truly open. We want to build a community. Okay. So, next up, I'm going to be welcoming our next speaker, David Salinas, to talk about another major feature that we are adding in AutoGluon version 1.0, which is AutoGluon Zero Shot. So, take it away.
Thank you. Yeah, that works. So I'm going to talk about pre-computed results, so we can generate all the set of evaluations, but I want to explain what we can do when we have so many evaluations in general. And then I will present some case studies, so how we use it for AutoGluon tabular. So in particular, how we use it to simulate lots of different methods to see how they work, and how to improve the final system. And finally, I will give you some bag of tricks, so that if you want to do the sort of approach, so generate lots of results, you can do it successfully for projects. So let's go for the motivation. We all know that, okay, so the compute per dollar is growing kind of exponentially with more law, but the cost of running experiment in ML is growing even much faster. So, we can look at ChatGPT and how many parameters it has, and we know that. But it's true not just for ChatGPT, it's true for NAS and so many domains. So for instance, you may all know that, but like the original neural architecture search paper, it requires 1,000 of GPU hours just to find one architecture on CIFAR10. And then obviously the authors could not compare, for instance, with random search, or not show that their methods were statistically better. So that's kind of unfortunate, but hopefully, as I will show, we can use pre-computed results and we can avoid those issues. So pre-computed results, it's about you evaluate many models on many data sets and seed. And so you don't throw that away, you just put it in a large table or database. So that's gonna be a bit costly. But then when you have new models, my slides are going down and down, so let me know if you cannot see it at some point. So when you want to train a model, you're gonna query this table instead of running the model from scratch, right? And of course, if let's say if the learning rate is slightly different, yeah, you could just use a surrogate model, so an XGBoost that's gonna interpolate, and yeah, so you use the result that comes out of your table or your surrogate model, and all right, so
yeah, that's what I was going to try.
All right. So then what can you do? So for instance, this NAS problem, that were like this reproducibility crisis, people have been using those pre-computed results, and they've been able to compare all NAS methods with an insane amount of seeds. So here you see a comparison like this, the distribution you obtain for all random search and I don't know, RL methods, and at a very statistically significant level. You can also perform meta-learning or transfer learning. So because you see so many of those data sets, there are lots of algorithms that you can apply that will say, you know, given a new data set, what would be a good configuration. And here I'm showing this figure from AutoScikit-learn 2, which used this technique very successfully, so that they could start with very good configuration instead from random one. And finally, we're using those pre-computed results. You can strengthen empirical analysis. So here I'm showing one example from a paper that got outstanding award in AUTOML. Where what they did is they evaluated 6 RL algorithms on all Atari games, but they run with 100 seeds, and they really analyze the result intensively. And there, what you can see, do I have? I don't know if I have. Oh, all right. Can you see my? Yeah, you can see my mouse. So here you see, for instance, the distribution of this the RQ epsilon, and you see the result that was reported. That would be a green light that I. But what you can see is, or maybe this is a better example, this orange, and then there is this line that was reported. So the line reported that's supposed to be the mean of the distribution is very far from the true mean of the distribution. So, and then they could say, you know, how many seeds you would need and so on. But then the thing is that you can reuse all that stuff and to compare new results. So current approaches for pre-computed results, so I mentioned a few, but essentially they're like all those sort of works that are there to increase the scope of empirical comparisons and allow to simulate methods for free. So people have been acquiring a lot of benchmark from NAS, but also this happens for like HPO, time series, reinforcement learning, and tabular prediction. Also, here I'm mentioning like systems that use pre-computed results, so not just transfer learning methods. So for instance, AutoScikit-learn 1 and 2 use it to improve their AutoML system, and also they were work using it for time series or for deep learning methods. Cool, so now for AutoGluon tabular, we acquired a big data set of pre-computed results. So we considered 200 data sets from regression classification multi-class. So thanks a lot to OpenML, because it would have been so hard otherwise. And so we evaluated 200 configurations for each framework. So for all those frameworks, we evaluate the configuration on all the data sets for 3 seeds. We also evaluated 6 AutoML frameworks for 1 and 4 hours fitting budget, right? So all those frameworks, and also AutoGluon for the 3 presets. So yeah, and so importantly, so for each of those evaluations, we store the performance metrics, but we also store the predictions. And so the reason we store the prediction is that then we can simulate in a very, very fast fashion any ensemble. We could not store the performance at every ensemble because that's exponential, but because we have the prediction of every model, we can simulate them for very, very cheap. So the downside is that we have a lot of data. So that's 4 terabytes of data and 200, and you need 200,000 hours of CPU compute. So 2 things I want to show. One is like you can now show how different frameworks perform if you were to tune them and ensemble them. I'm showing one way, but you could do any way you like to compare. So I'm going to show the CDF, so the whole distribution of normalized scores and ranks. So you're better when you're on the top left. So AutoGluon in black here is the best method. And you can see, for instance, in blue, you have cat boost, and dash line is when you tune the method. So the plain line is a default hyperparameter, and the dotted line is when you tune it with 4 hours of random search. So you can see that you cannot retune a method and outperform AutoGluon, so that was known. But maybe if we will ensemble the top 20, we'll get better. So what if we ensemble? And as I said before, because we store the prediction, you can do this plot for kind of free. And now you have still the dotted line that is like the tune method, for instance, for cat boost. But you also see like the result you will obtain if you will perform an ensemble on top. And you see that, well, you don't quite catch yet the performance of AutoGluon. So ensembling benefit to more from some framework than others. But the main message here is that, well, first you can kind of confirm what the AutoGluon paper show, that just tuning the framework is probably not sufficient. But also here to generate those results, you would have needed like weeks of compute at the very least. But it just takes like a minute or like a few seconds. Because you can just use these pre-computed results. Now the second part is hyperparameter optimization strikes.
One hyperparameter tuning.
Huh?
It's one hyperparameter tuning.
Yeah. And it's a revenge of it. Right. So before AutoGluon, as Nick said, virtually all frameworks, AutoML frameworks, use HPO. But strikingly, AutoGluon got very good result without HPO, with a heuristic that Nick talked about, so bagging, stacking, ensembling. But it's not that HPO does not help, it's just that it has a compute cost, and this compute cost is actually better spent on bagging, stacking, and ensembling, or training more models. But still, so AutoGluon has like something like 13 default models, and they are manually picked. And now the question, like, can we do better? And so, yes, we can learn the default with pre-computed result. So to learn the default, it's going to be a bit small, sorry for that. Essentially, you can select complementary configuration greedily. So you don't select quite the configuration that has the best average performance and then the one that has the second best performance, but you select them in a greedy fashion so that they have jointly a very good performance. I'm just saying it works because it's just two equations, and you could look at, for instance, AutoScikit-learn paper if you want to see this portfolio equation. But my point is it's very fast and easy to implement. And yeah, it's used by many other before successfully, so AutoScikit-learn 1 and 2, AutoPyTorch. Now I want to show the result if you do that with all those pre-computed results we gathered. So I'm going to show the result in a leave one out dataset fashion, just to say, so we are not cheating. So every time there is a dataset in our collection, we just use all the other to learn the portfolio. So we're not cheating this way, and we also restrict the time limit as the other AutoML system. If you do that, you will obtain those results, so zero shortest portfolio. And so if you think that you cannot hear, it's like, yeah, so this is where if you tune Cat Boost for 20 hours, I mean, that's a long time, but you can do because you can simulate. I mean, it's just stagnate, and it is worse than AutoML frameworks. However, like, so with this portfolio, you can see that you can outperform AutoGluon's best. So for all budgets except for 1 hour, but for 1 hour it's very close. And also in this case, we obtain this result without stacking, so you can see that the latency is much smaller. So yeah, so we can outperform AutoGluon best without stacking, so with just a config change. But the big thing is that because we have these pre-computed results, we can also look at many things. We can see what would happen if we would increase this time limit. So here we use 4 hours, but what if we put 24 hours? What if we will have less data set or more configuration? So those questions are rarely studied in transfer learning paper because it's so expensive to do those kind of comparison. But yeah, we can because it's basically for free. So here, for instance, it's the effect of the training time limit. So it's a bit small, sorry for that. But right, you see that the more time you spend, the better you get, which is not always the case of AutoGluon best, because you can see, for instance, between 1 hour and 4 hours, there is not a massive difference. But for those portfolio, it always helps. And with 24 hours, you can beat basically AutoGluon best in virtually all the dataset. But interestingly, you can see how much of this large collection of dataset was important. So for instance, if we were to have much less dataset, you can see the effect, so the performance kind of drop. But it is, you don't need 200 datasets, maybe you need something like 100 datasets where the performance saturates, and the same for number of random configuration. So before I go to the part like the bag of trick parts, like we can do a cost analysis. Of course, evaluating all those evaluations, that was expensive, so it's something like 200,000 CPU hours that we spent. But running all those experiments I've shown you, it's probably something that's, I mean, it's something that 5 million CPU hours. So there is a 20x saving right there. And of course, the ratio is only going to be larger as we use this dataset more, and maybe other people use it, like maybe yourself. Now, the last part is about just some tips that I want to share. In case you want to generate your next NAS4.1 benchmark or benchmark for, I don't know, for RLHF or something like that. So something that I think is very important is to evaluate the opportunity. So something like, how many persons will use your data set, and how many times maybe, how many times will you use it? So if you never use it, maybe no one will, right? And in particular, I'm saying this because if you're trying to anticipate how many person, beside you are going to use it, it's very heavy tail, so it's pretty hard to guess. But in particular, areas that are great potential fits, I think, as like when hyperparameters are very finicky. And I'm mentioning RLHF because we all know RLHF is so sensible to all those PPO hyperparameters. So it's clear that there are going to be nice paper around that. But also great potential areas like when the empirical evaluation typically have too little signal to distinguish the noise, and there you can think about reinforcement learning. Also, you can think about evaluating the cost of evaluation because, of course, you are balancing opportunities and costs. So what is the cost of running evaluation from scratch if you did not have all those pre-computed results? How many, what's the total cost, of course, that you're going to need, and what is the minimum cost that you could use to validate your hypothesis? So, for instance, for AutoGluon, for this tabular, we did not went all in with 200,000 hours of CPU compute, but we went much smaller to begin with. Last thing is I want to mention some engineering challenge. So, in my experience doing these things, the engineering effort has always been very underestimated. And so in particular, like you'll probably face some scaling issues. So you will have failures, so like some model evaluation fail. A lot of edge case, what do you do when evaluation fail? You can have out of memory for one configuration. At the end, if you collect lots of data, it's kind of a challenge to access gigabyte to terabyte of data. One thing that is often overlooked, but it's the evaluation speed. So how fast does it take to just get one number for the table? So it looks like stupid because, it's going to be less than 1 second. And if you do it for truly, it will be an hour. But the thing is, like for those experiments, for instance, you start to query your table like millions or billions of times. So it's actually important to have something that is, decently efficient. And so we did for this work in particular, we had to do many optimizations so that we could use it in a nice fashion. The second thing is like to keep iterating. So I think it's important to not try to anticipate all those kind of issues from the beginning of the project, otherwise you will over-engineer. But maybe you can think about fixing fires as they come, but just know that when you're planning that it's going to be a bit longer than maybe what you initially anticipate. And very often you will need several iterations in all the projects that I've seen that were until the end. We needed maybe at least 3 or 4 iterations. I think in this case we needed 4. So you can, so it's good to start small. Don't spend all your compute in your first iteration, but just increase progressively. And so to conclude for this part, so I showed a case study on pre-computed result for AutoGluon tabular. And so I hope I convince you how pre-computed results can be very useful, doing model comparison for free, including sampling, searching, or doing meta-learning. I show you that for AutoGluon, with just a config change, just changing the default parameters, we're going to be able to improve the system by a lot. So this data, we plan to release it. We don't have the date yet, so but we are planning maybe, I guess it will be some time around this year. But I also want to highlight that you can use this technique with pre-computed results and get probably very impactful results, or either for your research or for your organization. So before I finish, I want to mention some open question. I think an interesting aspect would be to have some scaling laws. So when you increase the size of your results, you certainly get improvements, but it would be interesting to have some idea about how fast the result improve. Probably there is an engineering question about general tooling. So everyone is doing his own framework and starting from scratch, but maybe there is something that we could share and reuse our team. And the last thing, it's a bit related, but it would probably be nice to have a one shop for all those evaluations, so they all live in different repositories. So and with very different, I don't know, technologies, and so it would be nice to have like one place to access them all. And yeah, that's it, I think.
Yeah, thanks, David, for the great presentation on this. This is something we've been working on for a long time now, even started last year. Just note, this kind of engineering effort and science effort takes a long time if you want to do it yourself. So we built this thing to be reusable and for the entire community to use it. Again, it's not available quite yet. We're still working on it, but you'll hear about it when we release it. We'll talk about it on Twitter, and it'll be in AutoGluon release notes and all that stuff. But you can think of it like, without even doing stacking, we were able to get a better result than AutoGluon's best, strongest configuration in less training time and faster inference. And we can just simulate this like millions of times faster than if we actually trained the models. And one thing is that we can take that solution that we found, and then we can stack ensemble it, and that makes it even stronger. We've tested this. I don't have numbers for you right now on that, but we're going to have something that I think is pretty strong for 1.0. And additionally, if you want to add, say, a new model to AutoGluon, right, and you want to like make the argument that, yes, we should add this new model as a default model to AutoGluon, what we can do is, instead of running the entire benchmark and training all of AutoGluon's models and this new model, and then ensembling them together and seeing if it helps, what we can do is just train that new model on all the data sets, and then put that results into this HPO, this basically simulation environment. Since we already have the results for all the other models, we can then just add this new model in as a new result, simulate, and see, does the simulator pick that new model in the best configuration, right? Does the simulator find that we're able to improve our best result by using that model? And that can be another way to accelerate the discovery of stronger models. Okay, so getting towards the end here, there's one last thing that I want to kind of tease, which is something I'm calling AutoGluon Assistant. So beyond AutoGluon version 1.0. We don't know exactly when this will become available. We've been working on it for a while now. But let's talk about this. Currently, AutoGluon is AutoML in 3 lines of code, as we can see. But what about AutoML in 0 lines of code? AKA AutoGluon, AutoML is so easy an AI can do it. Hi, AutoGluon. Build a predictive model that answers the question, what sorts of people were more likely to survive using passenger data from the Titanic, right? Just raw text, hey, solve my problem. And my problem might have messy data. It might be in multiple different tables. It might need to have certain columns removed, like an ID column. It might not be IID. Figure it out. So, you know, LLMs have been getting a lot of attention recently, and I think that we can use LLMs to empower AutoML systems, and that's what we've been working on. And one of our goals here, create the first AI Kaggle Grandmaster. Something that can look at a new Kaggle competition, the raw text provided by the business that basically is looking to get a good solution, and AutoGluon Assistant writes the code autonomously, loads the data autonomously, preprocesses it, trains models, returns a prediction, and submits, and is able to compete with very proficient data scientists. So it's too early to give full results now, but basically we are playing around with hundreds of Kaggle competitions and working on prompts to have an LLM work as an argument parser, basically look at all the information about a competition and generate the arguments necessary to basically write those 3 lines of code properly for the competition. But also, there can be more nuance to it, like ID columns, feature types, if there's multiple tables, right? So we're working on it one step at a time, But currently, we have satisfied the criteria to become a Kaggle Master, which is the tier right below Kaggle Grandmaster, and we're 60% of the way towards being a Kaggle Grandmaster so far. And it's going to be interesting. But one thing is when it comes to new data sets, right, that are very challenging, I think that this is the frontier that pushes things beyond what AutoML Benchmark, for example, has. Right? In AutoML Benchmark, it's like these clean data sets all in one table, IID, super nice to work with, not necessarily representative of reality. Whereas Kaggle, I would say, is much closer to reality and is also much tougher. So I think as the AutoML field matures, we should start trying to compare against the very best. And I think with LLMs, we can start writing tools that can actually tackle this kind of a problem with raw text. And I think it would lead us in a very interesting direction. So this is not something available yet, but it is something that we're working on and has been showing pretty promising results so far. So wanted to just mention this. So again, you can find AutoGluon at auto.gluon.ai. We have a cheat sheet. You can find the cheat sheet in our website. This is literally all you need to know to do everything you really need to do with AutoGluon. We have tutorials for everything. We're constantly updating things, improving, trying to push the state of the art, trying to make it easier for others to contribute. We're trying to build a community around this, a community of developers, making it so that it is as easy to contribute to and improve as possible. And we want to continue to push the state of the art for practical machine learning. So with that, thank you all for listening. And we can begin the Q&A section. And one final thing is everyone here is welcome to contribute. And also, we have a community Discord right there. If you'd like to join us, we'd be happy to have you. OK, so questions?
All right, thanks a lot to the team. I think it was a very interesting thing spanning quite some topics. I'm sure there will be some questions. Maybe while the audience can think about that, there was already an online question. And the question was, is there a way of using the lib to predict on repeatable time series? So multiple time series instances of the same repeated process, for example, drilling process in production, with the goal to predict a single target per instance?
Unfortunately, I'm not sure if I completely got the question. If you're talking about predicting multiple time series or like the same time series in multiple places, so essentially doing backtesting, that is definitely possible. There's information on how to do that in the tutorials for how to generate multiple validation windows from a single time series, and then you can just do a single call to predict or evaluate, and you will get the scores either for the backtest or the predictions for the backtest.
All right, thanks a lot. I think there was another question somewhere over there, right? So then let me, I think that's too much of a throw for me, sorry.
Hi, so my question would be about deployment. So I'm very much concerned with deploying machine learning to embedded systems, and very often there we have not only like the goal to maximize accuracy and stuff like that, but we also have like constraints, like the model has to consume less than X amount of memory, latency has to be below X and Y, so it's basically a multi-objective optimization problem. And also, depending on the target system, how to acquire such metrics, like how much memory does a model consume widely differs. So can I somehow communicate such a problem to AutoGluon to ask it to search for an optimized model for me?
So that's a fantastic question. And this is a very pertinent question when it comes to practical usage, especially when you have to deploy it on device, for example, right? Now, that is a challenging scenario that I think most AutoML systems aren't really tackling right now, but it is really relevant. So one thing is that you can optimize directly the inference time. Basically, you specify it as a constraint, saying, I require you to be at least this fast in inference. And then what we will do during training is we will dynamically change the models that we're training and basically how we're ensembling to basically ensure that we will meet the constraint, right? So that's called infer limit. It's a fit argument constraint. Now, you mentioned that there are a couple others, right? There's memory and disk, right? We don't currently have direct ways to optimize that exactly. However, that's a very good point and something that we probably want to add. I think that we do track disk usage and memory usage, basically how much memory and disk does it take when the model is loaded or like in disk. And so we track that for every model. And so post-fit, what you can do is you can look through those, and then you can select a model that basically has overall memory and disk usage within your bounds. So that's a way to do it, but we don't have a direct optimization right now. But it's definitely something that can be done. There's no inherent difference between doing that and doing like infer limit.
Maybe one small addition, at least in how we work at the moment is mainly that since our target system is sometimes a microcontroller and stuff like that, we can kind of like measure how much memory it will consume. We just often just need a way to kind of like send this back into the AutoML system. So sometimes it's not really about how to measure it, or we don't want to measure on the system we are performing AutoML. We kind of like have this information, we just need to feed it back.
Right, so I mean, we do have memory, we are memory aware when training, right? Mm-hmm. So we will avoid training models if it will go out of memory, right? And you can specify your memory threshold, actually, is one way of doing it. There's not a direct way where you say 2 gigabytes, but you can basically, there's a memory modifier that you can set, and then you can look at how much memory your total machine has, and then mess around that to effectively say you only have 2 gigabytes of memory or something. Mm-hmm. One thing also with dedicated systems is sometimes you can't run Python on them, and AutoGluon actually has a variant that doesn't use Python. Basically with PyODI, and I forget the exact things, but like we have like, you can run it like in a browser, for example, and then also we have like Onyx compilation support, so the final artifact can be in like Onyx where it doesn't need to run in a Python environment.
Thank you so much.
Yep.
Too much power. Thank you first of all for this great talk. I think it was very insightful and also very valuable to understand like the thinking behind the product of AutoGluon. So thank you first of all. My question goes a bit into the feature selection processes. You touched a bit on that when talking about the time series AutoGluon process. For example, you drop the duplicate columns, for example, as well as columns that do not have any kind of predictive power. Besides that, it looked like you just use all features as it is, or is there some other kind of feature selection process? And the second question, do you have like different feature selection processes for your different models? Meaning, for example, your stats sequential tabular, is there some specific strategies based on this, different segments of models?
Right, yeah, so that's a great question. So basically, we just use everything if it gets past the feature. But with that said, we have custom model-specific feature preprocessing, right? So there's a bit of nuance there. But in terms of the automated feature selection and pruning logic, so that's not enabled by default. It was an intern project a while ago, and it actually works quite well. We get about 60% win rate compared to current AutoGluon if we enable it. The reason it's not enabled by default is that it has some edge cases where basically if you have many, many features, it'll take longer than it ought to. And therefore, I wanted to avoid the worst case scenario of it being inconvenient to people, right? Even though the win rate's better. And so we're planning to revisit this for 1.0 to handle those scenarios and then enable it by default. The way it works is basically a naive implementation is that you have something like permutation shuffling feature importance, which you can calculate as a black box method per model. And then you can basically keep training the model again and again. And then every time you train it, you then look at the feature importance. You take the least important features, you remove them, you train it again, and you keep doing this until your validation score doesn't improve anymore, right? That gets really expensive really quickly. So instead, what we have for practical implementation is we have a proxy model like LightGBM that we just train, and then we just use the features that LightGBM finds to prune for all models. And basically, we train all the models with all the features, and then with the LightGBM prune variants of the features, and then we just kind of let the ensemble figure out whether to use the full version or the pruned version, and that's what ends up getting us at like 60% win rate. There's a lot of nuance there. You could choose different proxy models. You could do the expensive technique. Yeah, it's kind of an open area, but yeah, it's something that's important that we do want to revisit for 1.0.
Thank you very much. Definitely answers my question.
Also, thanks from my side. Great tutorial and great insights into AutoGluon. I have one question about AutoGluon Bench. And I really like this idea of having, in essence, A/B testing when people contribute to AutoGluon. But one thing that keeps, like, I was wondering is, how can you make sure that, assume we always test against the AutoML benchmark, that eventually we don't overfit on the AutoML benchmark when we just improve AutoGluon, right?
Right, and so I think that this is a very tricky problem in general. The one thing is that this requires a bit of human common sense going into it. You can't have fully automated where I take a nap and just let this thing commit things into AutoGluon and then just hope that it's all good, right? That's probably not like what's going to actually work. You're going to need to then like analyze, does it make sense why this is improving? Are the techniques being used general, or are you kind of just like looking at one of the data sets and doing a trick that only applies to that one data set and then it's better for that, right? The good thing about the AutoML benchmark, it's 104 data sets, 10-fold cross-validated, which is 1,040 tasks essentially. And that's pretty hard to overfit to in general. And we're looking to increase the size of that as much as possible. So for example, for that zero-shot work we did, we have over 200 data sets, right? And again, anytime someone says, here's a good data set, we want to add it, right? And on top of that, we have a lot of internal data sets too that, while we don't cover it in these talks, we also very closely look at the performance of those, and that's like hundreds or thousands of data sets in those regards too. But yes, there is a risk of overfitting, but it's kind of a necessary, like no matter what you do, yes, there's always going to be a risk of overfitting. The hope is that you have a large enough, generic enough suite of data sets that you avoid that risk, and that the things that you're implementing in the system are generic enough such that they won't realistically just be overfitting by, right? You have to justify what you're doing more so than just it improved the benchmark, right? You need to say fundamentally, why would you think that this would improve things, right? Yeah.
Thanks.
Yeah. And then
one final question. One final question.
So thanks, first of all. Question I have is on page 32, you mentioned that memory is the only failure, I guess. And one question I would derive from this is, does AutoGluon already support, or are you planning to support, streaming data sets that don't fit into memory?
Great question. So this has actually been asked before on GitHub. And so the answer right now is no, we don't have that planned for 1.0. With that said, we do support this in multimodal already, because multimodal models, generally speaking, they're these deep learning models that work in batches, right? So we do support it for multimodal. However, for tabular, it's very tricky. So the moment that you go into a data set cannot fit into memory, you get into a lot of tricky things. For example, global preprocessing. How do you do that? You'll need to do some kind of way where you have like staged information that you capture in what can be fit into memory, and then you keep track of that as you need to re-architecture the entire preprocessing logic for that. On top of that, for models such as XGBoost and LightGBM, you would need to run them on special low memory modes that basically load data into disk, which then slows down training immensely. So my general takeaway for anyone who wants to do larger than memory data, just get a bigger machine if possible, I would say. I mean, there are machines out there on the cloud that have 4 terabytes of memory, right? And then worst case scenario, if that's still not enough, just subsample your data. I think you'll be just fine. If you have that much data, you can probably sacrifice some of it and still get a good result. Yeah, so we aren't planning to support that right now, but I mean, if it's something that comes up as like a frequent pain point, definitely we'll take a look. Yeah.
Okay, thanks a lot.
Yeah. And then I would be remiss not to give Eddie his question. He's been raising his hand the whole time, so if we could.
Very cool work. Looking forward to it. Yeah, so you don't do any HPO, of course, but multi-objective optimization. So you still optimize for a metric, but in the actual ensembling stage or the stacking stage, do you still consider would it be possible to do multi-objective optimization there?
Certainly. I mean, for example, inference time, right, is one example, right? Currently, we do it as a constraint rather than a multi-objective optimization. I mean, you can create something like a Pareto frontier automatically. We actually have logic in leaderboard. You can actually call only Pareto frontier, and it'll show you like the Pareto frontier of things. With multi-objective, it's a little bit tricky because it really depends on what users are looking for. I mean, outside of, I guess, accuracy and inference speed, you know, maybe there are some others, but they're not super obvious that many people need those things necessarily. I mean, we can talk separately if you have some ideas, right? But I mean, into the whole HPO thing, right? So we are doing HPO in zero shot. That's the idea, though, is that we do the HPO offline so that we just have the good stuff for the user, and we can avoid the slowdown from HPO. Yeah.
Yeah, cool. Thanks very much.
Yeah.
All right, then let's join me in thanking the speakers again.